According to current scientific understanding, the universe has not always existed in its present form: space, time, matter, and energy all appear to have originated from a single early state. This event is known as the Big Bang. The term does not describe an explosion in space. There was no center. There was no surrounding emptiness. Instead, space itself began to expand. At the earliest moment science can describe, the universe was extremely hot and extremely dense. All matter and energy were contained in a state far beyond ordinary conditions. The laws of physics, as we understand them today, cannot fully describe this earliest phase. What can be described is what happened immediately afterward. As the universe expanded, it began to cool. Energy transformed into particles. Particles combined into simple forms of matter. At first, there were no atoms, no stars, no light, only fundamental particles, moving through a rapidly expanding universe. Within the first few minutes, conditions allowed the formation of the simplest atomic nuclei. Hydrogen began to appear. Helium followed shortly after. These two elements would later become the primary building blocks of stars and galaxies. At this stage, the universe was still opaque. Light could not travel freely. Hundreds of thousands of years later, the universe cooled enough for electrons to bind to atomic nuclei. This allowed the formation of neutral atoms. For the first time, light was able to move freely through space. This ancient light still exists today. It is known as the cosmic microwave background. The cosmic microwave background is one of the strongest pieces of evidence for the Big Bang model. It is detected uniformly in every direction, indicating that the early universe was nearly the same everywhere. Small variations within this background would later become regions, where matter slowly gathered over immense periods of time. Gravity amplified these small differences. Denser regions attracted more matter. Less dense regions became emptier. This process occurred gradually. There was no sudden structure, no rapid formation, only slow accumulation, guided by gravity. Eventually, the first stars began to form. These early stars were massive and short-lived. They produced heavier elements through nuclear fusion and distributed them into space when they ended. From this process, the material for future generations of stars, planets, and life became possible. The universe continued to expand, not slowing down, but accelerating. This expansion is driven by a phenomenon known as dark energy. Its nature remains unknown, but its effect is measurable. Galaxies are moving farther apart as space itself stretches. Throughout all of this, the universe follows the same physical principles. Energy behaves consistently. Gravity shapes structure. Time moves forward from a hot, dense beginning to a vast, cooling cosmos. The universe evolves without intention and without awareness. As the universe expanded and cooled further, matter continued to organize under the influence of gravity. Vast clouds of hydrogen and helium slowly collapsed inward. Within these regions, pressure and temperature increased. When conditions became extreme enough, nuclear fusion began. This marked the birth of the first stars. These earliest stars were unlike most stars today. They were large, extremely hot, and short-lived because the early universe contained almost no heavy elements. These stars burned their fuel rapidly. In their cores, lighter elements fused into heavier ones. Carbon, oxygen, silicon, iron, elements that did not exist before, were created inside these stars. When these massive stars reached the end of their lives, they collapsed under their own gravity. Some exploded as supernovae. In these events, heavy elements were scattered into surrounding space. This material mixed with interstellar gas, changing the chemical composition of the universe. From this point on, future stars would form from enriched matter. Over time, groups of stars began to assemble into larger structures. Gravity drew them together into rotating systems. These systems became galaxies. Some formed spiral shapes. Others became elliptical or irregular. Each galaxy contained billions or even trillions of stars. Between them, vast regions of empty space remained. Within galaxies, stars continued to form and evolve. Around many of these stars, disks of gas and dust developed. Particles within these disks collided and gradually combined. Small fragments became larger bodies. This process led to the formation of planets. Planetary systems are a natural outcome of star formation. They do not require rare conditions. Observations suggest that planets are common throughout the universe. Rocky planets, gas giants, frozen worlds, many exist in stable orbits around long-lived stars. In some regions, conditions allowed liquid water to exist. Where water is present, complex chemistry becomes possible. On at least one planet, this chemistry led to life. The mechanisms behind this transition are still being studied. What is known is that the materials required for life were produced by earlier generations of stars. As galaxies evolved, their interactions shaped large-scale structure. Galaxies formed clusters. Clusters formed super. Between these structures, vast cosmic voids developed. On the largest scales, the universe resembles a web. Filaments of matter surrounding enormous empty regions. Despite its complexity, this structure arises from simple principles. Gravity amplifies small differences. Expansion stretches space. Physical laws remain consistent. No guiding force is required. The universe organizes itself through these interactions over billions of years. Throughout this time, the expansion of the universe continued. Measurements show that this expansion is accelerating. Galaxies are not slowing down. They are separating faster. As time progresses, the cause of this acceleration is attributed to dark energy. Its origin and nature remain unknown. Dark energy does not behave like matter or radiation. It does not clump. It does not form structures. Instead, it affects space itself. As the universe grows larger, dark energy becomes more influential. Its effects dominate the future evolution of the cosmos. Even with these unknowns, much of the universe is understood through observation and theory. Telescopes detect light across the electromagnetic spectrum, from radio waves to visible light to high-energy gamma rays. Each reveals different aspects of cosmic processes. By studying this information, scientists reconstruct events that occurred billions of years ago. The universe leaves records of its history in light, motion, and structure. These records do not fade quickly. They persist across immense distances and long periods of time. As the universe continues to expand, stars will eventually exhaust their fuel. Star formation will slow. Galaxies will become quieter. Energy will spread more evenly through space. Change will continue, but at an ever slower pace. Nothing in this process is sudden. On cosmic times, everything unfolds gradually. The universe evolves without urgency. Its processes operate far beyond human lifespans. And yet, every atom in the present universe is connected to this long history. The matter that forms planets, stars, and living systems originated in earlier cosmic events. In this way, the universe carries its past forward into the present. As time continues, the universe becomes larger and less dense. Stars form more slowly, as available gas is gradually consumed. Existing stars age, changing as the fuel in their core is depleted. Small stars burn quietly for trillions of years. Large stars live fast and end sooner. Each follows predictable physical rules. In many galaxies, supermassive black holes exist at their centers. These objects formed early and grew as surrounding matter fell inward. They do not actively pull everything toward them. Only matter that comes close enough is affected. From a distance, they behave like any other massive object. Black holes are regions where gravity becomes extremely strong beyond a certain boundary, known as the event horizon. Information cannot escape. Light cannot return. What happens beyond this boundary cannot be directly observed. As a result, black holes represent limits in our current understanding of physics. Despite this, their presence is inferred through motion. Stars orbit invisible centers. Gas accelerates and heats up. Energy is released before matter disappears. These effects can be measured with precision over very long periods. Galaxies interact. Some pass by each other. Others merge slowly. When galaxies merge, stars rarely collide. Distances between stars are too large. Instead, gravitational structure changes gradually. New star formation may increase for a time, then decline. Eventually, most galaxies will become isolated due to cosmic expansion. Distant galaxies will move beyond the observable horizon. Their light will never reach us from any single location. The visible universe will appear smaller. Over time, energy continues to spread out. Temperature differences decrease. The universe moves toward a state of increasing uniformity. This process is slow, but constant. There is no final moment, only gradual change. On these scales, human concepts of beginning and end lose meaning. Processes do not stop, they fade. They stretch, they thin out. The universe does not require observation. To continue, it does not respond to awareness. Its behavior is governed by consistent relationships between matter, energy, space, and time. These relationships persist, whether or not they are noticed. Matter rearranges, energy transforms, space expands. This continues quietly, without interruption. As expansion continues, distances between large structures increase. Clusters of galaxies drift farther apart, connected only by the memory of earlier gravitational influence. On the largest scales, motion becomes less noticeable, not because it stops, but because everything is farther away. Stars that remain will slowly change. In smaller stars, fusion proceeds at a low, steady rate. They emit light and heat for extraordinarily long periods. Trillions of years may pass before they exhaust their fuel. Larger stars will have long since ended, leaving behind dense remnants. Some stars collapse into white dwarfs. Others form neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons. In the most extreme cases, collapse produces black holes. Each outcome follows directly from mass and gravity. Over time, stellar remnants cool, white dwarfs fade, neutron stars lose energy, black holes remain, changing only very slowly, through rare interactions or gradual evaporation. Nothing disappears suddenly. As fewer new stars form, galaxies grow dimmer. Their structure remains, but activity decreases. Spiral arms become less defined. Gas clouds thin out. The universe enters a quieter phase. Temperature differences continue to even out. Energy spreads across larger volumes of space. This process is described by the second law of thermodynamics. Entropy increases. Systems move toward equilibrium. In this context, complex structures become less common, not because they are unstable, but because conditions that support them become rare. Change does not reverse, it only slows. Time continues forward, without preference. There is no central clock, no universal moment. Events occur locally, each following the same fundamental principles. On these scales, the universe has no destination. It does not move toward a goal. It evolves according to conditions set long ago. Expansion, cooling, and transformation proceed together. Matter still exists. Energy still exists. Space continues to grow. Processes remain consistent. Even as their effects become subtle, the universe becomes simpler, not by design, but by natural progression. As the universe grows older, its large-scale structure becomes more defined. Matter continues to follow gravity, but opportunities for new structure decrease. Most of the universe is now empty space. Between galaxies, distances are so vast that interaction becomes increasingly rare. Within galaxies, stellar systems remain stable for long periods. Planetary orbits continue, with little change. On many worlds, conditions are cold and quiet. Energy arrives mainly from aging stars. Weaker than before, but steady, some planetary systems are disrupted. Over extremely long times, gravitational interactions slowly alter orbits. Planets may drift inward or be ejected into interstellar space. These events are uncommon, but inevitable given enough time. Free-floating planets move through galaxies. Without stars, they are dark, cold, and abundant. Though difficult to detect, they may be as numerous as stars themselves. In regions near massive objects, gravity continues to dominate. Stars orbit galactic centers. Matter occasionally falls inward, releasing energy before disappearing beyond reach. These processes occur quietly over millions of years. As star formation declines further, the universe transitions into a long period of low activity. This phase lasts far longer than all previous eras combined. Light becomes rarer. Most radiation shifts toward longer, lower energy wavelengths. Eventually, even the longest-lived stars approach the end of their fuel. They cool and dim. Without dramatic collapse, what remains are stellar remnants and dispersed matter. Chemical reactions slow. Complex processes become difficult to sustain. The universe does not become empty, but simpler. Structure remains. Motion remains, but change becomes subtle. Time continues to pass. Without interruption, no signal marks these transitions. They are gradual, distributed, and silent. The universe enters what can be described as a mature state, not ending, not static, but slowly evolving toward uniformity. As the universe continues through this long, quiet era, most remaining activity occurs on extremely small scales. Individual particles move slowly. Interactions become infrequent. Matter is spread thinly across expanding space, making encounters less likely with each passing epoch. In this environment, gravity still operates, but its influence weakens over distance. Bound systems remain intact, yet isolated. Galaxies that once interacted now exist alone, separated by expanding space that can no longer be crossed. Over immense spans of time, stellar remnants dominate. White dwarfs cool further, approaching the temperature of their neutron stars lose rotational energy, their signals fading into background noise. Black holes persist the longest. According to current theory, black holes are not entirely permanent. Through a process known as Hawking radiation, they lose mass extremely slowly. For stellar mass black holes, this takes far longer than the current age of the universe. For the largest black holes, the process may take trillions upon trillions of years. As black holes gradually evaporate, they release low-energy radiation. This radiation disperses into space, adding to the background energy of the universe. No dramatic event marks their disappearance. They simply diminish. Eventually, even these processes become rare. The universe approaches a state where meaningful interactions are extremely uncommon. Energy is evenly distributed. Temperature differences are minimal. Entropy is near its maximum. In such a state, change still occurs, but at a pace difficult to define. Quantum processes may continue. Particles may fluctuate briefly, then return to equilibrium. These events are local, temporary, and isolated. There is no darkness in the human sense. There is no silence to be heard. There is only a uniform, low-energy environment, stretching across expanding space. Time does not stop. There is no final moment. From any single point, the universe appears calm, nearly unchanging. Yet, on the most fundamental level, processes never fully cease. The universe does not collapse into nothing. It does not reset. It continues, simple, diffuse, and quiet. Even in this nearly uniform state, space continues to expand. Distances increase, not because objects are moving faster, but because the fabric between them keeps stretching. Expansion does not require energy from matter. It is a property of space itself. As space grows larger, the average energy per region decreases. Photons lose energy as their wavelengths stretch. Radiation becomes colder, longer, and less distinguishable from the background. Light still exists, but it no longer illuminates structure. Matter remains, but mostly as isolated particles. Protons and electrons drift through space, rarely encountering one another. When interactions occur, they are brief and leave little lasting change. On extremely long timescales, even stable particles may not be permanent. Some theories suggest that protons can decay. If this occurs, it happens very slowly. Timescales far beyond trillions of years. If proton decay is possible, then most remaining matter gradually transforms into radiation, and lighter particles, solid structure dissolves, without violence, not destruction, but conversion. As this process continues, the distinction between matter and energy becomes less meaningful. Everything that remains exists in simple forms. Motion persists, but without pattern. The universe does not become empty. It becomes sparse. It becomes uniform. It becomes quiet in a physical sense, not through silence, but through balance. There are no longer regions where complexity gathers, no stars to ignite reactions, no planets to sustain cycles, only space, expanded and cooled, holding the remnants of earlier eras. Yet, even now, fundamental laws remain unchanged. They do not weaken with age. They do not forget how the universe once was. They continue to apply to every particle, every region. Without exception, time moves forward. Without accumulation of events, moments pass, but nothing marks them. Change is so gradual that it loses definition. The universe persists, not as it once was, but as the natural outcome of everything that came before, and in this persistence there is no conclusion, only continuation, only duration, only space, time, and the quiet result of a long cosmic history. In this extended future, the universe no longer has eras in the traditional sense. There are no clear transitions, no events that separate one phase from another. Change happens continuously, but so slowly that it becomes almost indistinguishable from stillness. Quantum fields remain present everywhere, even in near-empty space. They fluctuate subtly. Pairs of particles may appear briefly, and then vanish again. These fluctuations do not build structure. They occur locally. Without memory, without consequence, space continues to expand. Regions that were once connected are now separated beyond any possibility of interaction. Causality becomes limited. What happens in one region has no influence on most others. The universe fragments into independent domains of existence. Energy remains conserved locally, but globally it becomes diluted. No region is energetic enough to initiate large-scale processes. No gradients remain to drive complexity. Everything approaches the same low-energy condition. Time, however, does not lose its direction. Processes, however minimal, still follow sequence. Cause still precedes effect. Even when nothing noticeable happens, time continues to pass. If space is infinite, this state extends endlessly. If space is finite, it expands without boundary. In either case, there is no edge to observe, no outside, no reference frame beyond the universe itself. What once were galaxies, stars, and planets exists only as histories. Their influence survives only in the distribution of particles and the geometry of space. Nothing records them directly. The universe does not remember. It does not archive its past. It carries it forward only through physical consequence. Every current condition is the result of everything that came before. In this state, the universe is neither active nor inactive. It simply is a vast, expanded system, governed by unchanging rules, operating at minimal intensity. There is no final equilibrium to reach. Expansion prevents completion. Uniformity increases, but is never absolute. Motion slows, but never fully stops. The universe remains open, not progressing toward an event, not returning to a beginning, continuing because nothing requires it to end. And so, across incomprehensible spans of time, space expands, energy disperses, and the universe persists in its simplest possible form. As the universe continues in this long, quiet state, something subtle becomes important. Although large structures are gone, and energy is evenly spread, the laws of physics still allow rare possibilities, not likely events, but possible ones. On extremely long timescales, random fluctuations can occur, not patterns, not cycles, just chance variations in energy and fields. Most fade instantly. A few last slightly longer. In a universe that exists for long enough, even unlikely events eventually happen, not because they are favored, but because time is abundant, almost unlimited. Quantum fields, present everywhere, never fully settle. They fluctuate endlessly. Even when conditions are calm, most fluctuations are insignificant, but some, in theory, could momentarily concentrate energy in a small region of space. If such a concentration were large enough, It could briefly resemble the conditions of an earlier universe, not a repetition, not a restart, just a localized event. With unusual properties, these regions would be extremely rare, separated by vast expanses of uniform space. They would not affect the surrounding universe. They would not spread. They would appear, exist briefly, and then dissolve. From the outside, nothing would seem to change. The universe as a whole would remain quiet, expanded, and nearly uniform, yet within it, isolated pockets of complexity might momentarily emerge. Another possibility lies in the geometry of space itself. If space is infinite, then all possible arrangements of matter occur somewhere, not often, not nearby, but somewhere, at some time. This raises a question that physics does not yet answer. Is the universe merely fading, or is it slowly rearranging itself in ways too rare to notice? If time has no end, then the difference between impossible and unlikely becomes less clear. Given enough duration, even order can briefly arise. From near uniformity, these ideas remain theoretical. No observation confirms them, but they follow logically from known physical principles. They suggest that the universe may never become entirely uneventful. Even in its quietest state, it may still contain the potential for surprise, not frequent, not dramatic, but persistent. The universe may appear finished, while still allowing new isolated stories to quietly begin. And if that is true, then this long future is not simply an ending phase, it is an extended middle, a vast interval where change is rare but not forbidden, which means the story of the universe has not concluded, it has only slowed, and what comes next is not something we expect to see often, but something that remains possible as long as time continues. If rare events can still occur, then the future of the universe is not completely uniform. It is mostly quiet, mostly empty, but not perfectly still. In some regions, a fluctuation may persist long enough to form a brief structure, not a galaxy, not a star, something smaller, temporary, a momentary imbalance. In an otherwise even cosmos, such regions would not announce themselves. They would not send signals across expanding space. They would exist in isolation, unseen, unrecorded. Their entire history could unfold without interacting with anything else. From a physical perspective, these events would be extremely inefficient. They would waste energy. They would not last, and yet they would still obey the same fundamental laws. If complexity can appear briefly, then disappearance is not the only outcome. Decay dominates the universe, but it does not forbid emergence. It only makes it rare. This introduces a subtle shift in how the future is understood. Instead of a smooth fade into uniformity, the universe may experience isolated interruptions, not reversals, not renewals, interruptions. In an infinite span of time, even the most unlikely configurations may form, not often enough to shape the universe. but often enough to prevent absolute stillness. Some theoretical models suggest that entire regions of space could briefly resemble a younger universe, hotter, denser, more active. These regions would be small. Compared to the whole, they would not expand outward. They would collapse back into the surrounding calm. From within such a region, time would feel normal. Processes would unfold according to familiar physics. If complexity were possible there, it would not recognize how temporary its existence was. This leads to an unsettling idea. The universe may be old, cold, and sparse overall, yet still capable of producing isolated moments that resemble beginnings, not a single beginning. Many, scattered, unrelated, unaware of one another. If this is the case, then the universe does not have a single timeline. It has countless local histories, most of them short, most of them unnoticed. From the outside, nothing changes. From the inside, everything matters. The universe does not favor these moments. It does not guide them. They are consequences of time without limit and laws without exceptions. This suggests that the story of the universe is not a straight line from order to disorder. It is a long decline with occasional deviations, rare enough to ignore, but persistent enough to never fully disappear, which means that even now, long after stars and galaxies have faded, the universe may still be capable of producing something unexpected, not nearby, not soon, but somewhere, at some time. And if such events can happen, then the universe is not simply aging. It is waiting, not for a purpose, not for an outcome, but because time continues, and possibility has not been exhausted. The quiet future, it seems, may still contain the seeds of stories that have not yet been told, and that means we are still far from the end, as these rare events remain possible. The universe carries a quiet tension. Nothing is building toward a climax, yet nothing is entirely settled. Time keeps opening space for outcomes that are unlikely but never forbidden. In most regions, nothing happens for spans of time longer than any earlier era. Particles drift, fields fluctuate weakly. Energy remains evenly spread. From almost every perspective, the universe appears complete. But completion is not the same as finality. Completion describes structure. Finality would require an end to process, and process, at the most basic level, never fully stops. Some fluctuations may become slightly more organized than others, not enough to form stars, but enough to briefly resist uniformity. A short-lived pattern, a temporary asymmetry, then equilibrium returns. These moments leave no trace. They do not accumulate. They do not connect. Each is isolated in space and time, like a thought that forms and fades without memory. Yet their possibility changes. How the universe must be understood. A future without events is different from a future where events are merely rare. The second is never truly empty. If time stretches without bound, the universe explores Every allowed configuration, no matter how improbable, not efficiently, not evenly, but inevitably. This does not mean renewal is coming. It does not mean collapse or rebirth. It means the universe remains open, even when almost nothing is happening. What appears calm is not locked. What appears finished is not sealed. The laws that shaped stars and galaxies are still present, still valid, still permissive, somewhere, at some time far beyond prediction. Conditions may briefly align, not long enough to matter globally, but long enough to form a local story. From within that story, the universe would feel active, time would seem meaningful, change would feel important, and nothing inside it would reveal how rare it truly is. Most of the universe would remain unchanged, unaware, indifferent, yet still hosting these isolated interruptions in its long, quiet future. This is not an ending. It is a prolonged middle, stretched across unimaginable duration, a state where decay dominates, but possibility remains. And as long as possibility remains, the universe has not finished speaking. It has only lowered its voice. Lowering its voice does not mean falling silent. The universe continues to operate at levels too subtle to dominate attention, yet too persistent to disappear. What changes is not the presence of activity, but its scale. Earlier, entire galaxies defined the rhythm of time. Later, individual stars carried that role. Now, the universe measures itself in far smaller movements, single particles, minor fluctuations, brief alignments. In this extended middle era, nothing competes for dominance. No structure lasts long enough to reshape its surroundings. Everything that forms exists locally, briefly, and then fades. Yet these fleeting structures share an important property. They follow the same rules that once governed stars and planets. Cause and effect still apply. Energy still transforms. Time still orders events. Even when outcomes are small, the framework remains intact. This consistency matters. It means the universe has not entered a fundamentally different mode of existence. It has not broken. It has not simplified its laws. Only its expressions have become rare. Because of this, any structure that appears, however briefly, is not an anomaly. It is a valid outcome of the same physical principles that shaped everything before. Most of these outcomes vanish unnoticed. They do not connect, they do not repeat, but they demonstrate something important. The universe has not exhausted its range of behavior. If time continues indefinitely, then the difference between has happened and can happen grows smaller, not in frequency, in inevitability. This does not suggest a return to a lively cosmos. It suggests something quieter, a universe that occasionally experiments within its limits, without consequence, without memory. From the outside, nothing appears to change. From the inside of a rare fluctuation, change would feel immediate. Growth, interaction, direction, all the features once common, compressed into a short span. These moments do not build a future. They do not accumulate history. They simply occur, then pass, and so the universe continues, not toward an ending, not toward renewal, but through a long interval where potential outlives prominence. The story is not advancing quickly, but it is not finished, because as long as time flows and laws remain unchanged, the universe retains the ability to surprise itself, and somewhere in this vast, quiet duration, that possibility is still waiting. Waiting does not imply intention. The universe does not anticipate outcomes. It does not prepare conditions. Possibility exists simply because the rules allow it, and time provides room. In this immense duration, probability becomes a different concept. Events that would never occur within the lifespan of stars become conceivable across spans without limit. Rarity loses its finality. Most configurations remain unrealized, but some, by chance alone, align briefly, not enough to change the universe, but enough to momentarily interrupt its uniformity. These interruptions do not resemble the past exactly. They are not echoes of galaxies or replicas of earlier structures. They are simpler, smaller, but still ordered. In such regions, gradients briefly exist. Differences in energy, differences in density. Where differences exist, processes follow, even if only for a short time. Within those limits, complexity can appear, not sustained, not widespread, but real while it lasts. This raises a deeper question. If complexity can arise again, even briefly, what separates an ending from a pause? If the universe never fully forbids structure, then decline is not absolute. It is dominant, but not exclusive. There is no cycle here, no rhythm. These moments do not repeat on schedule. They occur without pattern, without memory of each other. From one perspective, they are meaningless. They leave no lasting mark. From another, they are everything, for within them, time regains texture. Events matter locally. Change becomes noticeable again. Nothing outside these regions responds. The surrounding universe remains vast, quiet, and indifferent, yet it does not prevent these brief deviations. This suggests a universe that never fully resolves into stillness, not because it resists equilibrium, but because equilibrium does not prohibit motion entirely. The future, then, is not a single outcome. It is a wide interval where almost nothing happens, and occasionally something does. The story does not move forward quickly. It drifts, but within that drift there remains space for unexpected detail, and as long as detail can appear, the universe has not reached its final form. It is still unfolding, slowly, quietly, and with more remaining than it reveals at first glance. What makes these rare moments interesting is not their size, but their contrast against a universe that is almost unchanged. Even a small deviation becomes meaningful. A slight imbalance, a temporary structure, a brief sequence of cause and effect. In these moments, time feels different. Not faster, but noticeable again. There is a before and an after, a direction, a sense that something is happening. This alone sets them apart from the surrounding calm. If such a region were large enough and lasted long enough, simple processes could unfold. Energy could flow, structures could interact, patterns could briefly persist. Nothing permanent, nothing expansive, but enough to resemble the early stages of organization. From inside such a region, the universe would not feel old. It would not feel exhausted. It would feel active, responsive, and open. There would be no indication that this activity is rare or temporary. Outside this region, nothing reacts. The larger universe does not adjust. It does not respond or compensate. It remains quiet, vast, and unchanged. These moments are contained, self-limited by surrounding conditions. This creates a strange situation, a universe that is overall near equilibrium, yet locally capable of brief departures from it, not enough to reverse the trend, but enough to interrupt it. Such interruptions do not accumulate. They do not build toward a larger event. Each stands alone, separated by immense distances and longer stretches of time. Still, their existence changes. How the future must be imagined. The universe is not moving toward a single final state. It is approaching a condition where almost everything is settled, but not everything is impossible. This distinction matters. A universe where nothing can happen is finished. A universe where almost nothing happens is not. As time continues, these rare events become the only sources of novelty, not frequent enough to dominate, but persistent enough to never fully disappear. The universe, then, is not telling one long story. It is hosting many short ones, scattered across space and time, most of them never intersecting. Each begins quietly, each ends quietly, and between them, the universe remains as it is, calm, expanded, and waiting not for a conclusion, but for the next rare alignment that turns stillness, just briefly, into motion again. These rare alignments do not announce themselves. They emerge quietly, without warning, within regions that otherwise appear no different from the rest of space. For a brief span of time, conditions shift just enough to allow structure to form. In such a region, energy does not remain evenly distributed. Small gradients appear where gradients exist. Motion follows. Particles interact. Fields respond. Processes unfold in sequence. Nothing here violates the long-term direction of the universe. These events do not reverse expansion. They do not reduce entropy globally. They exist within limits set by the surrounding calm. From within, these limits are not obvious. Processes proceed normally. Time feels continuous. Causality remains intact. There is no signal that the surrounding universe is older, colder, and quieter. If the region persists long enough, complex arrangements can briefly arise. Not large-scale structures, but organized interactions, patterns that hold together for a time before dispersing. Eventually, the imbalance fades. Energy spreads outward. gradients flatten, the region returns to the same low-energy state as its surroundings. No trace remains. No marker in space or time indicates that anything occurred there. From the outside, the universe continues unchanged. Yet, the possibility remains, not as an expectation, but as an allowance. As long as the laws of physics remain consistent, they permit these deviations. This means the universe never fully settles. It approaches stillness, but does not seal itself against motion. The difference is subtle, but important. A sealed universe would be final. This one is not. Across vast expanses of time, these brief stories continue to appear. They do not connect, they do not accumulate, but they ensure that the universe never becomes entirely eventless. Most of existence remains quiet. Most regions remain unchanged, but not all. And so the universe continues, not toward a single ending, but through a prolonged state where near completion coexists with rare interruption. The story has slowed, but it has not stopped. It persists, thin, quiet, and open, as long as time itself continues. Because these interruptions leave no trace, the universe does not accumulate memories. Each event is isolated, not only in space, but in history. What happens in one region does not influence what happens elsewhere. There is no continuity between them. This isolation gives the universe a fragmented future, not one unfolding narrative, but countless short sequences, each beginning and ending, without reference to the others. In most of space, nothing distinguishes one moment from the next. Time passes, but without milestones. Expansion continues. Energy remains diffuse. From almost every location, the universe appears unchanged. Yet the rules remain active. They do not weaken with time. They do not become selective. They continue to allow motion, where conditions briefly permit it. In rare regions, those conditions align again. A slight imbalance forms, not dramatic, not sustained, but enough to create a brief sequence of events. Within such a sequence, cause and effect regain clarity. One interaction leads to another. A direction emerges. For a short span, the universe behaves as if complexity still matters. These moments are fleeting. They end quietly. As gradients dissolve and energy disperses, no boundary marks their conclusion. They simply blend back into the surrounding uniformity. Nothing prevents this process from repeating elsewhere, not often, not predictably, but without limit. This gives the universe a subtle kind of persistence. Not persistence of structure, but persistence of possibility. Even when almost everything is settled, not everything is closed. The future, then, is not empty. It is sparse, filled mostly with quiet, and occasionally with brief alignment. Each alignment is small. Each is temporary. But together, across endless time, they ensure that the universe never fully resolves into stillness. The story continues, not as a single thread, but as scattered fragments, appearing and fading within an immense, calm background, and as long as time extends forward, those fragments remain possible, waiting not to be found, but simply to occur. Occurrence does not require observation. These fragments of activity do not need to be seen to take place. They unfold whether or not anything is aware of them. The universe does not distinguish between witnessed and unwitnessed events. Because of this, most of what happens in the far future will never be known, not hidden, but unconnected. No signals travel far enough. No records persist long enough. Each event exists only for itself. This absence of connection changes what continuity means. There is no grand sequence, no accumulation of progress, only repetition without pattern, emergence without memory, yet within each brief alignment, the same structure of time applies. There is a beginning, there is development, there is resolution. Even if all of this happens on a minimal scale and a short duration, from within such an alignment, the universe feels active, processes interact, outcomes follow causes. Nothing suggests that this activity is rare across time. Nothing indicates how isolated it truly is. Outside, the larger universe remains unchanged. Expansion continues. Energy stays diffuse. Most regions never experience any noticeable deviation. This contrast persists indefinitely. Near total stillness, punctuated by rare motion. Uniformity, interrupted by brief structure. The universe does not prefer one state over the other. It allows both. Most of the time, the conditions for activity are absent. Occasionally, they are not. As time extends further, these rare moments do not become more frequent. They simply remain possible. Their probability does not vanish. This means the universe never reaches a point of complete inactivity. It reaches a state where activity is no longer dominant, but not forbidden. The story, then, is not one of revival or collapse. It is one of persistence. The persistence of rules, the persistence of time, the persistence of possibility. Nothing dramatic awaits. No final event, but also no absolute silence. The universe continues as a vast background of calm, occasionally giving rise to brief local stories that appear, unfold, and quietly dissolve. And as long as time continues, those stories remain part of the universe, not connected, not remembered, but never fully absent. When everything is considered, the universe does not move toward a dramatic ending. It moves toward quiet, but quiet is not the same as nothing. As time stretches far beyond familiar scales, most structure fades, energy spreads, differences disappear, change becomes rare. From almost everywhere, the universe appears finished, yet it never fully closes itself. The same rules that once allowed stars, galaxies, and life continue to operate. They do not promise repetition. They do not guarantee complexity. They simply allow it, under rare and temporary conditions. Because of this, the future is not empty. It is sparse, mostly calm, occasionally interrupted by brief alignments where motion, structure, and causality return for a time. These moments do not save the universe. They do not reverse its direction. They do not build towards something larger. They exist, and then they end. There is no memory between them, no progress, no grand continuation, only isolated stories, appearing within an immense background of near. This is not a cycle, not a rebirth. It is persistence without purpose. The persistence of time, the persistence of physical law, the persistence of possibility. A universe where almost nothing happens is still different from a universe where nothing can happen, and ours never becomes the latter. So the story does not conclude with silence, nor with renewal. It settles into something quieter than both, a vast, calm expanse, where change is rare, local, and fleeting, but never completely gone. And as long as time continues, that is enough for the universe to remain unfinished